As you know, momentum, right? It's just the momentum of an object is the mass times the velocity. And we've been writing that as P equals mv. Right, so that's the momentum of an object. So for reasons that will make sense momentarily, let's find the rate of change of momentum. Okay, well, the rate of change of anything is you take it's like time derivative, like velocity is dx dt and acceleration is dv dt. So the rate of change of momentum is going to be dp dt, so that's the rate at which it's changing. Well, what that means is we then need to take the time derivative of mv. So we'll take d by dt of mv. So we're taking the derivative of two things that are multiplied together. So now it's time to flex your new calc skills. Product rule, okay, because we're taking the derivative of two things that are multiplied together. Well, so let's go with this. So that's going to be, right, the derivative of the first times the second, dm dt times v, plus the first times the derivative of the second. Well, let's pause and look at this and see what this means. First of all, this first term, dm dt. Well, that would mean that the mass of something is changing. So in general, when we're talking about how something's going to move, often for us, this is often zero. Usually the mass of something isn't changing. Now, when's a case when the mass of something could be changing? Classic example is a rocket. So that, in fact, is why this term, kind of physics slang, this is often called the rocket term. Because then you would have a dm dt, you know, as the rocket's losing mass as the fuel's burning. Another time when this could be relevant is when something's like moving through like a cloud of like dust and like collecting it. So then that would be a case where you have a changing mass. But often we'll throw this away. Well, so if you look at what's left, you've got then that dp dt. So let's just do one more line with this. dp dt equals mdv dt. Right? But what's dv dt? The rate of change of velocity is the acceleration. Oh, so that's ma. Oh, but that's force. So it turns out, and I'm going to write it down here, dp by dt, the rate of change of momentum, that is just the force. So this actually is the original version of Newton's second law. What it's saying is that if you want to change the momentum of something, if the momentum is changing in some way with time, you must be putting a force on it, right? So if this is zero, if the momentum of an object's not changing, you must not be putting a net force on it. Just a new little way of thinking about this, okay? So again, the rate of change of momentum is the force. You have a larger force, you'll have a larger change in the momentum of the object in a given amount of time. So just rearranging this thing a little bit, like if I kind of bring the dt over to the other side, okay? Well then from this, and I am going to just erase this to clear up some space. So let me get rid of rocket term here. So from this, what we can see is that if you just move the dt over the other side, you have, well, a little itty bitty change in momentum is equal to force times a itty bitty change in time. Well, so this is an itty bitty change in momentum, and this is an itty bitty bit of time. Well, if you sum up over the itty bitty changes in momentum, right, then you'd get the total change in momentum. So this is delta p, right? The meaning of this, well, I'll rewrite it, it's integral f dt. But what this would be is the area under a force versus time graph. Okay, So it turns out this is very, very useful. If you have a graph of the force that's on something as time goes by, the area under that thing is just going to be your change in momentum, right? By the way, this isn't that new because, as you know, if you had, and this picture might get a little bit small, but let's just try it anyway. If you have an acceleration against time graph, right? Say you have that. Here's say the acceleration of something as a function of time. Well, you know, if you find the area under it, the area under an acceleration graph, that's going to be your delta V, your change in velocity, right? Well, if you just multiply this by m, so you make an MA graph, which is really a force graph, versus t, let's just make the same graph, really, right? MA. Well, if the area under A versus T is delta V, then the area under MA versus T must be M delta V. So the area is M delta V or delta P. So the area under this guy, so it's really not that new what we're doing here. M delta V, or that's equal to change in momentum, right? Because you have a mass times a change in velocity. So what that means is, if you actually are able to measure the force as a function of time and take the area under it, you've just learned the change in momentum of the object that's, you know, for which the force upon it is being graphed. Now, one last thing I have to add here. Okay, so our two big takeaways are going to be this thing, that force is rate of change in momentum, and then the other takeaway is going to be that the area under force versus time is the change in momentum, right? Now, this is unfortunate, but it's a notational thing, and I don't know the history of this, but for some reason, somebody has decided to make a symbol for the change in momentum. That's called the impulse, and they've denoted it with a capital J. Okay, this is what's called impulse, but it really is just this. So anytime I see this, I just immediately translate in my mind to it is just the change in momentum. Okay, this isn't one of those cases where I'm trying to say like, oh, for you guys, you can think of it as the change. It's not that you can think of it as the change in momentum. It just is the change in momentum. So big take-home point is that if you can have a force versus time graph and you find the area under it, that's going to be the change in momentum. Well, so let's play around with a specific example with, you know, kind of using this thing, using these ideas, okay? So if we look at the little plot that's underneath, it says you hit a 100-gram golf ball with this force. So just to understand what's happening here, right? At time t equals 0, there's no force, and the force just starts to build. So this is when the club makes contact with the ball. So the club meets the ball. Let's just say it that way. Okay. On this whole bit here, the ball is like, the club's coming in and it's hitting the ball, so the ball's kind of like getting compressed, like against the club face, and the force is kind of building up. So the ball is getting compressed. Okay, this is basically where the max force is. You can see it. Then, now the force starts to decrease. Well, that's because you've brought the club in, bam, it's hitting the ball, it squeezes it. Well, now the ball's going to start to leave the club face, right? And so then the ball is starting to, you know, I'll just say the ball is leaving the club face. And here's where it actually loses contact. So, you know what, I might even just do it this way. Here, we'll just say the ball loses contact with the club. Right, so when you just bash something, you first make contact with it, the force builds and builds, gets to a maximum, and then the object starts to leave the club, and then right when it loses contact, the force then it has to go to 0. Okay, so that's kind of what's going on here. And it says, okay, so you hit a 100-gram golf ball with this force, and it wants to know the speed of the ball after the impact. Well, what we basically just learned is here we're given a force versus time graph, so the area under it, under F versus T, I could have just written area, I guess, but let's roll with this. F versus T. That is your delta P for the golf ball. All right, so let's get the area. So we gotta figure this out. So the area under this thing, well, it's half the base times the height. So half the base is 0.01, so 1/100th, and the height is 900. So the area under this thing is actually just going to be 9. Now, 2 ways to get the units. One is for the rest of your life, to know what the area, the units of area under a graph are, you can just multiply the units of this axis by the units of this axis, right? Because that's what the area is going to be. So it is going to be newtons times seconds. But you can also realize that it's also supposed to be change in momentum. So you can also give it units of momentum, which is mass times velocity, or kilogram meter per second. So that's your area under F versus T, which is delta P, which then needs to be M delta V. Right. Well, so it looks like all we got to do is divide by the mass, and we'll learn the delta V for the golf ball. And what is this thing, 100 grams? So we got 0.1 kilos, delta V. So it looks like we just gotta divide this by 0.1, which is like multiplying by 10. So 90 meter per second, getting close to 200 miles an hour. So that golf ball was properly struck. That's your delta V of the golf ball.